Yeah. Nice catch. Okay. So yeah, so we're gonna go through review the master theorem a little bit. So it has 3 conditions. So first of all, we need to check the relationship between Fn and the polynomial function, which is n raised to the power of logarithm base b of a. Okay, so this constant logarithm base of b is basically the thing you want to compute out of this a and b, and then you compare the 2 functions, which is f of n and the polynomial function n to the power of logarithm base b of a. Okay. So the first condition says if the polynomial function is a upper bound of f of n, and that is to say the polynomial function grows faster than the f of n, then the solution t of n is bounded by the polynomial function. That's the first condition. And it has some technical details that we need to define some constant epsilon so that the polynomial function is a upper bound, but that upper bound is a polynomially bigger upper bound or polynomially higher upper bound. So we'll see a counter example that's in some cases this function can be a upper bound, but that upper bound is not polynomially higher than the f of n. Okay, so in this case, that's the case 1. And in the second case, the 2 functions, the f of n and the polynomial function, they have the equal asymptotic property. That is, they grow equally fast. Then the solution is the polynomial term times the logarithm of n, right? And the third case is that the polynomial term is the lower bound. And that also comes with a extra condition, extra detail that this upper bound is also a polynomially lower upper bound, and some additional regularity condition here. Then the solution is bounded by the f of n. Okay, so without diving into the details, we can basically have the idea that master theorem basically compares 2 functions, which is the f of n attached here and the n to the n raised to the power of logarithm b of a, which is a polynomial function. So whatever is larger or whatever has a higher order among these 2 will determine the solution, determine the form of the final solution. Okay, but now we are going to look at the technical details, why we need such epsilon conditions here. All right, so yeah, we've been through this. Last time we have played this. So the technicality is that in case 1, the function f of n should be smaller than the polynomial function, but it should be polynomially smaller. Okay, so it must be smaller for a factor of n to the power of epsilon. And this epsilon can be really small, can be any value, but there should be an epsilon. Okay, and basically in case 3, it is also the same similar case. The fn should be greater than the polynomial function, but it also must be polynomially larger. Okay, and the case 3 has one more regularity conditions, which is that the A times f of n over b should be smaller than c times f of n, and c is a constant smaller than 1. And this condition is something you can check really quick once you know the form of f of n, right? But this is actually usually satisfied by most of the polynomially bounded functions. Okay, so actually we don't need to worry too much about the regularity condition, but it is really case 1 and case 3 that we need to satisfy that one is either smaller than the other or greater than the other by a factor of polynomial term. Okay, if that condition is not satisfied, then we should not use master theorem. Okay, master theorem doesn't apply to all cases, so there's still some limitation here. All right, so let's look at some cases. So the three cases do not cover all the possibilities of the function f of n. Okay, and there's gaps between case 1 and case 2. When, for example, the f of n is smaller or grows slower than the polynomial function, but not polynomially smaller, or it's greater but not polynomially greater. Okay, so whenever the function falls into these gaps, we should not use master theorem. Okay, so we actually know about this, have gone through this example last time, right? So in the maximum subarray problem or merge sort, they have basically the same form of recurrence. We have a equals 2 and b equals 2, right? And the function f of n is a linear function, okay? So in this case, the logarithm of base b of a is a linear function. So the f of n and the polynomial function, they grow equally fast, which means we need to apply the case 2. And yes, so I found a question that the logarithmically greater is not polynomially greater. Exactly. So a logarithm function grows slower than any kind of polynomial function. So if a function is logarithmically greater than the other one, then that doesn't fall into either case of the master theorem. So yeah, I think this is the example we're gonna through. A equals 2, b equals 2, so the polynomial term is a linear function, right? A linear function. But when we compare the linear function with the f of n is n times logarithm of n. It is indeed, this one is indeed a upper bound for this polynomial function, right? But this upper bound, or let's say this lower bound is not a polynomially significant or polynomially lower bound for the f of n. So why? Because we cannot find a epsilon that makes the function f of n to be greater than c times the polynomial function by a polynomial factor here, right? Because if so, right, if we can find a polynomial, we can find some constant, we can find some epsilon such that the function on the left is greater than the function on the right, then we can eliminate n, which results in that a logarithm function is greater than some polynomial function, which could never satisfy it. A logarithm function is always grows slower than the polynomial function, no matter how large what kind of values epsilon is, as long as epsilon is greater than 0. Okay, so for this recurrence, we cannot use the master theorem. Okay, So this is the one example showing that this particular recurrence falls into the gap between case 2 and case 3. It seems like case 3 applies, but indeed it doesn't apply. Okay. And there are other examples here, and we can quickly go through them. In this case, a equals 9, b equals 3, so the polynomial term is n squared, which means it is a upper bound for the function f of n. So case 1 applies, and the final solution is determined by the quadratic function. Okay, and also we can find the epsilon here, right? Because the quadratic function is polynomially bigger than the linear function, right? When epsilon equals 1, this applies. When epsilon is it's even more true when epsilon is smaller than 1. Okay, let's consider another recurrence. So here a is 1 and b is 3/2, right? And if we take the logarithm of base b of a, it is 0, and that means the logarithm function, the polynomial function, and the f of n, they are actually equal functions because they are all constants. So case 2 applies, right? That's one example. And for this example, this is a bit tricky here. So because when a is 3 and b is 4, so the logarithm of 4, logarithm with base 4 of 3, we know that it must be less than 1, right? Because the 3 is smaller than 4. So if we use a calculator, find its value, it's almost this number. So this is the approximated number. It's not the exact precise value. But now we can use this number or this value as a way to determine whether it is a case 1 or case 3 to fit with the master theorem. Okay, so the f of n is some linear function times a logarithm function. Okay, so is this a upper bound for the polynomial function here? Right, that's something we need to check. Okay, so because this value is smaller than 1, right? In one of the previous examples, we have shown that if this is a linear function, then this combination is not polynomially greater than the linear function, right? So what we need to have is that the coefficient here should be smaller than 1, right? So as long as the coefficients, let's call it y, okay? If the y is smaller than 1, then after we eliminate the y here, then the resulting coefficient here is 1 minus y, right? And we want to show that the upper bounds, this upper bound is satisfied, right? So because when the epsilon equals say 0.220, then this value becomes 1, right? And if this value, the index exponential term becomes 1, then this quantity, this inequality is never satisfied. because we know that a logarithm function is never faster, is never polynomially faster than a polynomial function. Okay, so in this case, we can indeed find that F3 case 3 applies if we can also show that the regularity condition holds. Okay. So, and the regularity condition, as it says before, that it is typically correct to any kind of polynomially bounded functions. So as long as we can find that, find the C that satisfy the condition, then we can basically prove that case 3 is true. Okay, so in this case, we can solve the inequality and find that if C equals 3/4, the inequality for the regularity term applies. Okay. So I guess this is the most tricky example in this case, but the overall principle is that we need to do the computation. We compare the polynomial function log the n to the power of logarithm base b of a and the f of n function, and we need to make sure that either one is greater than the other one with some polynomial epsilon, with some polynomial coefficient epsilon here. Okay. So next we're gonna see why master theorem will work. Okay. So master theorem is not actually self-explanatory. It is just a statement, and we didn't know why this is the case. Okay, so if we want to see why this is the case, we will show that in this proof that actually we can draw some tree-like structures. We can use the recursion tree method that we used in the previous lecture to basically conduct the proof and to get some intuition of why master theorem will work. Okay, and I think we have mentioned a little bit about the form of the solution using recursion method, and in this in the next couple of slides we will see that actually the solution to a theorem, it actually consists of two parts. The first part is the cost for solving all the smallest cases, all the subproblems in the smallest size. And the second component, the second part, is all the cost of doing the dividing and combining steps. Okay, so we proved the master theorem with two steps. With two lemmas. We first want to prove lemma 1. So lemma 1 reduces the problem of solving the recurrence to a problem of a mathematical expression that contains a summation. And in lemma 2, we basically determines the upper bounds and the lower bounds of this summation. Okay, and lemma 1 says that, so for a that's greater than 1 and b that's greater than 0, then we let f of n to be a non-negative function determined on the exact power of b. So this is for simplification because each time we will divide the problem into n over b. So when n is defined on the exact power of b, it will make the proof easier. So of course this is approximation. So the proof we show today is not the complete form of proof, but I think this incomplete kind of proof is sufficient to show the ideas behind the master theorem. Okay, so this is the form of the recurrence. and we let the basic case to be constant running time, and we have Fn and A times T of n over B, okay, which is what we already know. Okay, then lemma 1 says that if we have a recurrence in this form, then we can write the solution in this form. The solution has two parts. The first part is the first part is here, the polynomial function. The slides are not posted. Is posted in the previous module, in the same module. Right? So the first part is the polynomial function determined by logarithm base b of a. Okay, and the second component here is a summation form of a kind of series, but we don't know what kind of series it is. It contains some f function, right? We don't know if it's a geometric series or not. And of course, ideally, we want some geometric series so that we know the closed form of it and we can solve its upper bound and lower bound. Okay, so that's how we got. That's the statements of lemma 1. So this is what we want to prove. We want to show how we get from here to here, right? And we'll use recursion tree, okay? Because a recurrence like this can be expressed by a recursion tree. So the first node, the root node, is here. It is f of n. And we know that it has a branches. So here we only draw 3 branches because we don't know, it's just for demonstration. We know that there are a branches each time we split the problem into subproblems. And the second level, in the second level here, the size of subproblem is n over b, right? Because that's the result when we substitute n over b into the original recurrence. Right, that's that's n over b, okay? And each split has a branches, okay? And if we look at the subproblem here, it is, it actually should be, let me see. It should be n over b squared, actually. So I will fix this. So the a's in the nodes here, they are typos. Okay, so it really shouldn't be a here. It really should be n here.
Is that from the book itself? Because I see errors like that in the book all the time.
From what?
Is that from the book? Because I see like stuff like that from the book all the time.
Yes. This is from the book. That's the same visualization. So actually, the a here should be n's. Okay. So like the way we did use the recursion tree method to prove a very concrete example of recurrence, we also tried to use the same method to find the solution to this recurrence. So remember, we need to look at the summation at per level, and then we need to determine how many layers or how many levels are there in this recursion tree, right? So in the first level, it's f of n, right? And the second level, it's a times f of n over b, because there are a branches and each branch is n over b. And next, it's a square, because each splits, the number of nodes grows by the factor of a, and the size of the subproblem decreases by a factor of 1 over b. Okay, so we can see that at any depth that's above the bottom level or the leaf nodes level, there's a to the power of j nodes, and each node has a cost of f of n over b to the power of j. Okay, that's something can be inferred from the forms of the recurrence. So we now simply need to sum up all the costs for all the nodes. So the leaf nodes are the special case we need to consider, because leaf nodes are where when the subproblem size reaches 1. Okay, so we can use this equation. When the size equals 1, we can solve j to be logarithm base b of n, and that's the leaf nodes. Where the leaf nodes are at, they're at the depth logarithm base b of n. Okay, so and there are that many leaf nodes, a to the power logarithm base b of n. So then we switch the base and the number within the logarithm function. It becomes n to the power of logarithm base b of a. So this is where the quantity log n to the power of log base b of n comes from. It is actually the number of leaf nodes. Okay, and since our since the problem tells us that each leaf nodes, each subproblem, the smallest case subproblem costs constant time to solve. So the total cost for all the total summation for all the leaf nodes is big theta of n to the power of logarithm base b of n, b of a. Okay. And for the internal nodes, we mean everything above the leaf nodes. They are the internal nodes. Okay, they have particular values associated to each node, which is a times a to the power of j times f of n over b to the power of j stuff. Okay, and the depth ranges from 0 to the level above the bottom level, above the leaf node level. Okay, so the summation of all the internal nodes is the summation of all the per level summations. Okay, we know that for each level, the summation is in this form, and the level ranges from 0 to logarithm base b of n minus 1. Okay, we're counting towards from the root node to the one level above the leaf nodes. Okay, so we just need to sum up these two parts. Okay, the leaf nodes parts and the internal parts, and that gives us the solution to the recurrence. Okay, so that's lemma 1 proved. Okay, so we've got a lemma 2 to prove. So because our goal is to find the upper bound of this solution T of n, right? Give me a second. Someone's knocking my.
All right, boys. Let's just do this ourselves now. Who wants to go first?
Sorry, guys. I will be back in 5 minutes. I need to print out something for my daughter. I will be right back. Sorry about that. All right, my apologies.
Man, that was quick. Like, do you have like a laser printer or something?
A laser what?
Like laser printer?
Didn't get it.
I don't know.
All right. So let's carry on. Anyway, our goal is to show the upper bound and lower bound for T of n. So now we just need to consider the asymptotic property for this function, right? We just need to consider, actually looking at this expression, we kind of have the idea that we need to compare the two parts. So whichever part that is in higher order will determine the property for this one, for the solution, right? So if this part is at a higher order, then it is the determined item. If this solution is the higher order term, then we will use that to determine the final solution. So now we simply, well, I would not say it's an easy step, but the idea is clear that we need to basically determine that we need to find whether we can have a closed form for this summation term. Okay, so that's what lemma 2 will need to do. Okay, so the meanings behind these two terms is that the logarithm of the n to the power of logarithm base b of a is the costs of solving all the smallest subproblems, because remember that's the summation at the bottom level, and this right part is the summation for all is the summation of all the nodes, of all the internal nodes. And we know that the internal nodes represent the costs of dividing and the combining steps. Okay. So actually, what master's theorem does is to describe how the total cost is distributed among the leaf nodes or the internal nodes. Okay, so in case one, the case one of master theorem says that the polynomial function is a upper bound, then it apparently tells that the dominant part is the leaf nodes. Okay, and case two tells that the cost is evenly distributed among leaf nodes and the internal nodes. Okay, and K3 is the opposite. It says the internal nodes or the root node is the dominant term. Okay, so now basically what we want to do is to know the upper bounds and lower bounds for this pretty ugly summation term. Okay, so that's what lemma 2 says. Okay, and let's g of n to denote this very big summation term. Okay, so what lemma 2 says that then if the f has the logarithm, has the upper bound in this form, n to the power of log base b of a minus some epsilon for some epsilon, then the whole thing is determined by the polynomial function. If they are equally fast, then g of n is in this form, the polynomial times logarithm of n. And if the regularity condition satisfied for c smaller than 1, then the function can be represented by the f of n term. So that's basically what lemma 2 said. It's already very similar to the form of master theorem. Okay, so this part is optional. You don't need to like remember how, or need to like totally understand how the proof is going on. But I think it's interesting to go through the details. because it tells that it has some interesting mathematical transformation showing how we can determine the upper bound, lower bound for each item in the series, and then the total summation for the series is naturally apparent. Okay, so for case 1, we says that the condition is that the f of n has the upper bound in this form, right? So it basically says that for each, if we substitute the n over b to the power of n over b to the power of j into this form, right? We can have the form in this one, like this one, right? And we substitute it into g of n because g of n contains a summation of bunch of these terms. Okay, so we substitute it into g of n, and the final form looks like this, right? But here there's some simplification we can do, right? We can move the exponential terms around. We can move the numerator and the denominator around by showing that it actually can be transformed into this one, and it's already some promising results because it looks like a geometric series. Okay, and some further simplification, we have a much simplified form with b to the power of epsilon to j. Okay, and this one can be the summation of a geometric series can be replaced by the formula, right? We know the formula for the summation of geometric series, and it's again in this form. Okay, so we can see that it is it has the upper bound of logarithm n times n raised to the power of logarithm base b of a. Okay, so it's quite easy actually from the condition here to here actually, right? We simply replace each term in the summation with its upper bound, and we can naturally get into a form of a geometric series or something. Okay, so that's case 1. And for case 2, and we use similar tricks because the case 2 says that the f of n and the logarithm and the function n to the power of logarithm base of b of a, they have equal asymptotic property. So we do the same substitution here, right? And this time it's a bit easier. Because there's no epsilon, okay? And the inside term also becomes a very much easier term because this one turns out to be 1, and it's turns out to be a constant, which is n the logarithm with base b of n times the n to the power of something. So it's a polynomial function times a logarithm function form. Okay, so this one is much easier than the case 1. And if you look at the case 3, case 3 says a regularity condition here, right? A regularity condition is like this, and we also need to use some substitution tricks, right? We let n to be n over b and substitute into the two sides. We would have a series of inequalities, okay? And we can basically multiply both sides of all these inequalities, and we can eliminate those terms. And it will become something like this. Okay, so this is inequality we want to use. Okay, and we substitute this whole this inequality into each term of this of the g of n function. We would have something also nicely done to a very neat geometric series. Okay, and it is upper bounded by the function here. So we have lemma 2 also proved by basically transforming the summation from lemma 1 into some geometric series, or it has a lower bound or upper bound coming from the summation of geometric series. Then combining lemma 1 and 2, we can show that this is actually the final form of master's theorem. Okay. The epsilon basically deals with the in order to make the summation of geometric series valid. Okay, so that's why these epsilons exist at the first place. Okay. So anyway, the master theorem, the point of using master theorem is to solve the recurrences quickly. So given a form that satisfies the a times t of n over b, you can quickly use master theorem to get a solution. And it is not required to know how exactly the theorem is proved, but the main idea is that it is the recursion tree method that we actually relied on to coming up with the solution. So that's pretty much what we have for the master method. So and we are almost done with the divide and conquer algorithms, and it's a very commonly used algorithm. So for the sorting algorithms, basically all kinds of sorting algorithm that runs with n times logarithm of n efficiency running time. It's basically based on the divide and conquer thoughts. And next, I will use the rest of our time to go through a very classical application of divide and conquer algorithm on the problem of matrix multiplication. Okay, because this problem is a very practical one. It is used frequently nowadays, not just in algorithm studies, but it is indeed a very commonly used algorithm in a lot of realms like data science, in machine learning. Wherever data needs to be represented by matrices, then the matrix multiplication problem is just a very very frequently used operation. Okay, so let's look at the problem. Given two matrices, capital A and B, and we simplify the question by using square matrices only. And the task is to compute the product between the two matrices. So the product between two n by n matrices is also an n by n matrix. Okay, and each element in the resulting matrix is defined in this way. Okay, the i's column and the i's row and the j's column elements in C is the summation. It's kind of a dot product between the ith row of A and the j's column within B, right? And we sum up all the product between aik and bkj, and k ranges from I to n. Okay. So that's the mathematical definition of matrix multiplication. So there are n square entries that we need to compute, and each entry is the summation of n values in this form. Okay, so a brute force algorithm is to use a triple for loops, right? Because we need to go through all the rows and all the columns in the final returned matrix, right? So the triple for loops here, the most outer for loop I iterates over the n rows, okay, and the inner parts go through n columns, and the most inner for loops is the loop for computing the elements at the position I, row I, and the column j. Okay, and within that for loop, we accumulates accumulates all the products into the elements Cij. Okay, so it's easy to guess how much running time we need for this triple nested for loops will cost us, right? We know that one for loop is a linear running time, and the two-layer for loop is a quadratic running time. So the triply nested for loops is basically a cube running time, right? And it's a function of n to the power of 3. Okay, so we want to see whether divide and conquer algorithms can help us save us some time rather than this cube function, because it's pretty expensive, right? We cannot stand a n square quant function, not to mention a cube function. Okay? So we start with some simple thoughts that if the dimensions of the matrices they can divide it by 2, then we can divide the matrix, divide the n by n matrix into 4 sub-matrices, right? Each small sub-matrix is in n over 2 by n over 2, right? In this form, and we give these sub-matrices some subscripts. We call the upper left corner is A11, the upper right is A12, right? Lower left A21, and lower right is A22. So having these sub-matrices, we can rewrite the equation of the matrix multiplication into this form, right? And the matrix, the products of sub-matrices also follow the rules of the matrix production. Okay, so C11 is the results of taking the first row in A and compute the dot product with the first column in B. Okay, a dot product means that we times A11 with B11 plus the result of A12 times B21. Okay, so that's why we have C11 here. And for C12 and C21 and C22, we have similar rules. We just take out the corresponding row times with the corresponding column in B. That's how we get all the solutions to the sub-matrices. Okay, so we can see that there's a sort of a divide steps, right? We divide the original problem into actually 8 smaller problems, right? We have 1, 2, 3, 4, 8 subproblems of conquering the products of between submatrices. Okay. So it's a smart way, but we'll see that this is not necessarily the ideal solution here. Okay, so let's call it a square matrix multiply recursive algorithm that solves the method in the recursive style. Because it's a divide and conquer way, we are solving the problem that's within the smaller instance. That's of a smaller size, but it's basically the same instance of the original problem. Okay, so we create some space to store the results, right? And we also define the base case, so the recursion will return at this step. So if we are computing the product between two scalar numbers, then we simply return the results. There's no way to split, right? But for any larger cases, A and B and C, we need to do the partition. Okay, so the partition is also not cheap, because we're dealing with matrices. We need to allocate spaces, and we need to specify the indices. So that's the cost for the dividing. Okay, and within each subproblem, we need to call the function itself recursively, but only on smaller cases here. Okay, that's a conquer and a combine step. Okay, so if we analyze the running time of it, we need to consider the cost of the divide, right? We are creating 12 new smaller matrices, because we are splitting each matrix into 4 smaller cases, right? And we need to copy all the original entries to the new matrices. It will cost us quadratic running time, because its matrix, the size n, the size of the number of elements in the size n matrix is n squared. Okay. So we can use the index calculation trick instead of actually copying into physical memories, but we can represent a submatrix by a range of row and column indices, so that the dividing step will take us constant time. So that's some trick we can use, right? We remember the indices of the elements of the boundaries, but don't actually copy the elements. So that's something we can save in running time. Okay. So in a base case, the running time is constant, right? But in the recursive case, right, we now simply decide running time, the size of the smaller subproblem, which is n/2, right? And there are 2 of n/2, right? So in total, we have 8 n/2 subproblems. Okay. And also, the amount of time for adding 2 n/2 by n/2 matrices should also contribute some cost. So the combining step is time costly, because the summation of matrices, it's inevitably quadratic running time. Okay, so the time step, the time cost for the combining step is big theta of n squared. So in total, we have our recurrence in this form. The original solution is big theta 1, that's the cost for dividing. That's the cost for solving all the subproblems recursively. That's the cost for combining step. So in total, we can write it in this way, right? So putting together, we have something like this. Right? We have A and B defined. So all we need to know is to all we need to do now is to use the master theorem, right? We have A equals 8, B equals 2. So the logarithm of base B of A is 3. So the polynomial function is n cubed, n to the power of 3, which is the upper bound for which is larger than the f here. F is a quadratic function. Okay, so that means the solution is big theta of n cubed. Okay, which is disappointing because we have spent so much time like splitting the matrices and doing the combination, and turns out that it is no better than the straightforward triple for loops method. Okay, so here so far, using the example, we've shown that applying a straightforward divide and conquer algorithm doesn't necessarily have better time efficiency, right? But in the case of matrices, matrix multiplication, we can think of some ideas of how to improve this algorithm, okay? Because the running time is dominated by the term here. It is the cost of solving all the sub problems, okay? And it turns out it is the cost of the bottom level of the leaf nodes, okay? So whether we can reduce the A's here is the key to improving the next, to improving the algorithm, right? Because the A equals 8 means that each time we do the split, there's just 8 resulting subproblems. And this kind of a tree, recursion tree, is very bushy. So the resulting leaf nodes will be a lot. So we basically need to make the tree less bushy so that the time efficiency can be improved. So there's something proposed by the Strassen's algorithm. It's quite smart, but I don't think it's intuitive. But as we go through these algorithms, you will see that it really follows the idea of reducing A to a smaller constant by improving the algorithm's running time. So it tries to make the tree less bushy. So instead of performing the 8 recursive multiplication of the sub matrices, it performs only 7. Okay, that sounds impossible, but actually with the usage of some intermediate variables, it is still doable. Okay, it is reachable, approachable. So it comes with some cost of solving some new additions of the n smallest sub matrices. Okay, it's not intuitive or not obvious at the first glance. So we'll go through the algorithms really quick and to see how it achieves this goal. So first, we just do the split as we did before. This takes us constant time. And we need to create 10 matrices from S1 to S10. And each of them is the sum or difference of the two matrices resulting from step 1. Because summation and subtraction takes constant time, takes quadratic running time. So we'll mark a big theta of n squared here. And step 3, we will use the S creating the step 2 to recursively compute 7 matrices products from P1 to P2. Okay, so here's the difference. Previous in the straightforward divide and conquer, we need to compute 8 product. Here we compute 7 products, which is obtained by a recursive call. So here we makes the recursive call on one less branch, right? Makes each division one less branch. And finally, we compute the desired submatrices using the results from the previous step, using the P's to compute the C's, which also takes quadratic running time. Okay, so let's look at the recurrence of the Strassen's algorithm. Okay, so for the base case, it is the same as it is just a scalar multiplication. It's constant time. So for recursive case, bigger case, the quadratic running time, the Strassen's algorithms recurrence is 7 times n to the power n of n over 2, t of n over 2, plus some quadratic function that include the cost of 1, 2, and 4. Okay, so this is already good news for us, because if you compute the master, use the master theorem, logarithm of base 2 of 7 is slightly smaller than 3. Okay, even though it's slightly smaller, but when the matrix grows very big, this will save us significant amount of time. And the state of the art for matrix multiplication can reach even lower using even smarter techniques. But the Strassen's algorithm is one of the earliest and the most classical algorithms. Okay, so we'll go through the details really quick. So the divide is the same as the straightforward recursive way. And step 2, we need to compute S1 to S3, S1 to S10. So these are our choices. And later on, you will see why we choose to compute these subtractions and summations. Okay. Anyway, we just need to know that this will cost us big theta of n squared running time. Okay. And the step 3 is to compute 7 products instead of 8 products of the between the S and the A's. Okay, so this is the actual computation here. We are not computing these forms directly, because the S, they are already computed in the previous step. Okay, but here these are just the explanations of what S is. Okay, that's P1 to P7. Okay, so next, the final step is to use the P's to compute the target's submatrices C11, C12. Okay, C11 is defined by P5 plus P4 minus P2 plus P6. Okay, it is in this form. And if we align these P's, we'll see that they eliminate each other, right? All these product terms with positives and negatives, they eliminate each other. And the resulting term is only 2 terms, A11 times B11 plus A12 times B21, which is exactly the form, which is exactly the definition of C11, according to the principle of matrix multiplication. Okay, and similarly, C12 is P1 plus P2, because we can eliminate A11 and times B22. Right, that's also the definition of C12. And for C21, similarly, we have its definition. And for C22, it's the summation and subtraction between 4 matrices. Okay, and the result is also exactly how we need to compute what we need to compute the C22. So that's all these steps combined, we are able to achieve the multiplication between two matrices within this, with the running time described by this recurrence. We have 7 as the A constants. Therefore, the dominant term is n to the power logarithm base 2 of 7. So that's the example of Strassen's algorithm. And I know it's a bit fast when I go through these slides. So hope you can read the slides after the video lecture ends. And the textbook contains more steps than the slideshow, but I think the slides here are clear enough to show the details. And not sure if the textbook contains other examples. But anyway, this is the first time I saw this algorithm, I think it's amazing because it's not incredibly straightforward, but it solves the problem of reducing the branches within the recursion tree in a really smart way. And nowadays, I'm not sure what kind of optimized algorithm is used in the matrix or in the linear algebra software packages used in, say, Python, NumPy, R. But this kind of optimized algorithm also comes with the price of lower numerical stability, because when you do too much matrix subtraction and addition, there's higher chance you lose the numerical accuracies in it. So there's always a trade-off between accuracy and efficiency. Okay. So anyway, that's the what we have for divide and conquer algorithms. And then in the next class in this week, we're gonna enter our next topic. If you have questions, you can raise it now or come to my office hour tomorrow afternoon, and I will send out email notifications about the new office hour. And we will have 2 office hours in a week. I will host one of them, and the other one will be hosted by the TA.
I want to ask you a question. So, since there's no pseudocode for this, are you going to ask us to create pseudocode for this on a test, or is this?
You mean the pseudocode for
the Strassen's algorithm?
Strassen's algorithm. Actually, the pseudocode is actually shown in the slides. I think it'll be interesting. It's quite interesting to read, but you don't need to implement it yourself with the pseudocode.
Okay. And just for reference, because I know you talked about the first day, so the tests are going to be time tests, or did you say they're going to be like take-home tests where you have to submit it at a certain time?
You mean midterm and the finals?
Yes.
They will be on papers.
Okay. Now, is there like a time limit to them for the day, or no?
What? Your microphone, I didn't hear it clearly.
Oh, I'm sorry. Is there like a time limit?
There will be a time limit.
Okay.
Yeah. You should download the PDF version of it, print it out, and finish it on paper and upload it within a limited amount of time.
Okay. So it's one of those. Okay.
Yeah.
But it's not gonna be like during class, right?
No, it's like offline one.
Oh, okay, perfect. Thank
Yeah,
you.
you don't need to turn on your Zoom to do that.
Hey, Professor, I just had a quick question.
Mm-hmm.
For the fourth question on the assignment, I was wondering when it asks you to prove that the function is within big theta of n to the d, do you want us to find like the coefficients like we did in lecture 2?
Yeah.
Or just, okay,
Yeah. You need to basically find the C's.
okay, great,
Yeah.
thank you.
Wait a minute, like you can't just like expand it out and says the last term is like n to the d, like that like proves it.
Yeah, you need to span it out and use some way to find the C1, C2, and then N0.
Oh wait, no, because I thought since since you had like a summation, you could just expand it out, and since the last term is n to the d, that proves the equation. Because wouldn't that make most sense?
Didn't hear your second half quite clearly.
Is my mic not working?
Yeah, there's some very loud background noise in your mic.
Okay, it's better.
Can you say your question again?
Okay. No, so we can just like expand out the summation, and like because I remember expanding out like summations, the last order term is what big O is, because if you expand out all the terms.
Yeah, I'm expecting to see more mathematical. So how you can show that mathematically the higher order term, the highest order term is the determinant term, dominant term.
Okay, so we can't just say that it is because
Yeah.
like a proven rule, so we have to actually show it.
Yeah, I would like to see some more actual proof of it.
Oh, okay. That's fine, I guess.
All right. Yep. Thank you, guys. I will see you tomorrow in my office hour. Thank you for coming.